You know about speed limits, right? The ones you see on the highway. But what if I told you the universe has them too? And even crazier, so does your own brain. Today, we are diving deep into the wild and surprising connections between speed limits at the cosmic scale and the ones hardwired into our very own biology. Let's get into it. I want to start with just a number, 50 joules. Now, on its own, that probably doesn't sound like much. But this wasn't the energy of a car or a ball. This was the energy of a single, solitary subatomic particle that came screaming into our atmosphere.
That's right. Imagine the kinetic energy of a baseball whipping past you at 95 kilometers per hour. Now cram all of that energy into a particle way smaller than an atom. So how is that even possible? This incredible discovery, back in 1991, handed physicists a puzzle of cosmic proportions.
And here it is. Meet the oh my god particle. I'm not kidding, that's what they called it. It was a cosmic ray with an energy so ridiculously high, our understanding of physics said it just shouldn't exist. It was like it was breaking the universe's own speed limit. So, if it broke a rule, what exactly is that rule? Well, think of it as the universe's toughest traffic cop, one you absolutely can't avoid. It's got a mouthful of a name, the Greisen-Zatsepin-Kuzmin limit. Let's just call it the GZK limit. It's a theoretical cap, a ceiling on how much energy a cosmic ray proton can hold on to after traveling across immense cosmic distances. Anything above that energy level should get hit with a cosmic speeding ticket. So what's enforcing this law? It's not a wall or a barrier. It's something that's literally everywhere, the cosmic microwave background, or CMB. This is the faint, ancient radiation left over from the Big Bang itself. It fills every nook and cranny of the universe. So here's how this traffic stop works. You've got this super-fast proton zipping through space. As it travels, it's constantly bumping into these low-energy photons from the CMB. When a proton is going that fast, the collision is so violent it actually creates brand new particles. And doing that robs the proton of some of its energy, effectively putting the brakes on. Over millions of light years, these tiny collisions add up. It creates a sort of cosmic fog. And what this means is that any proton traveling with energy above that GZK limit should get slowed down if it comes from too far away. Specifically, farther than about 160 million light years. It should run out of steam before it ever gets to us. And yet, we saw it. That oh my god particle made it all the way to Earth. So that's the paradox, right? We have a rule that makes perfect sense, and then we have what looks like undeniable proof of that rule being broken. Now, this wasn't just some minor academic debate. It was considered one of the great unsolved problems in modern physics. Scientists were seriously asking themselves, how is it possible for these particles to show up on our doorstep with energies they just shouldn't have? And it wasn't a one-off. The oh my god particle got all the headlines, but other experiments started spotting more and more of these rule breakers. These observations were flying in the face of what we thought we knew about how the universe works. Okay, I want you to hold that cosmic thought for a minute. We're about to do a hard pivot. We're going to zoom all the way in from the vastness of outer space to the space right between your ears, because it turns out your own body has to deal with its own fascinating speed limits. Just like the cosmos has laws for how fast particles can travel, your nervous system has its own set of rules for how fast information can move. It's a completely different scale, but you're about to see how the problem and the solution is surprisingly familiar. Every single thing you think, feel, or do comes down to your nervous system sending signals. It does this with tiny electrical impulses that race along specialized cells called neurons. It's basically a biological information superhighway. The signal travels down this long, cable-like part of the neuron called an axon. You can think of it as a biological wire. But here's the thing. It's not a perfect conductor. It has resistance, the signal can leak out. There's a very real physical limit on how fast that impulse can travel. So our bodies have a speed problem. How do you get a signal from your toe to your brain fast enough to pull your foot away from something sharp? You need to beat the lag. And evolution came up with an absolutely brilliant shortcut. This is it, the myelin sheath. It's a fatty layer that wraps around the axon, kind of like the rubber insulation on an electrical cord. Its entire job is to stop that electrical signal from leaking out and losing its punch. And the difference this insulation makes is just incredible. A neuron without it is slow, but you wrap it in myelin, the signal speed becomes dramatically faster. We're talking about an upgrade from dial-up internet
to a fiber optic line. It's a total game changer for rapid response. Just look at how nature uses it. The neurons that have to send signals over really long distances, like the ones for your senses and muscle movements, they're myelinated. The shorter range neurons, not so much. It's a perfect example of nature using this clever biological hack exactly where it counts the most. Okay, let's bring it all back together. We've seen a speed limit in the cosmos and a speed limit in our own biology. And what connects them is this amazing theme of limits and the clever loopholes you can find to get around them. Both systems are running up against fundamental physical constraints, but neither the universe nor evolution just throws in the towel. They find loopholes. Myelination is biology's loophole. So what was the loophole for the oh my god particle? Well, scientists came up with 3 main possibilities. First loophole, maybe these things aren't protons at all. Maybe they're heavier atomic nuclei, like iron. Those are tougher and can survive the journey better. Second loophole, maybe their source is actually much closer, just inside that 160 million light-year boundary. Third loophole, maybe our early measurements were just a bit off. And you know what? The most recent data we have strongly suggests it's loophole number 1. And this really gets to the heart of it. When you find an apparent paradox, a broken rule like the GZK limit, it doesn't mean physics is wrong. It's an invitation. It's a big, flashing clue telling us that our understanding isn't complete and that there's a deeper, more fascinating reality waiting to be discovered. From the fatty coating on a single neuron to the composition of particles from faraway galaxies, these limits are what drive innovation and discovery. And it really makes you wonder, doesn't it? What other fundamental limits are out there just waiting for us to find the loophole?